All right, let me hand out, so I printed the cheat sheet, I guess, for this chapter, everything you need to know roughly. So I'll hand that out. No, I did not get a chance to post new notes. Oh, okay. All right, and then before we get started doing these practice problems, and actually I'll try to, I know you guys like the notes, let me try to export a PDF while I talk. So I'm wearing my obnoxious green shirt today to remind you to register. And so maybe you saw that on the announcements, but basically they've only given us one lab section again. I don't think that we're going to fit into one lab section, at least I hope not. So usually people drop from Chem 221 to 222, but I usually don't lose anyone from 22 to 23. But they're not going to give us another lab section unless we all sign up and force them to, basically. So please sign up. And then they didn't put a time for the class for some reason. I'm not really sure why, but I figure we can chat about the time. I don't know if you like this time or if we should move it back to what it was first quarter, which I think was starting at 10 a.m., but I don't know what your classes are taking. So is that a no to the 10 a.m.? So this is a better time for people? Okay, I'm seeing a lot of nods with this being the good time. So we'll stick to this kind of compressed schedule, but it sounds like it works for y'all so it doesn't conflict. So yeah, I'll set the time as the same with the 11:30 lecture and then recitation right after. I'll have to see what time they put the lab at, but we'll kind of set up the same Tuesday, Thursday thing. Again, sign up so we can be like, yes, we do need 2 lab sections.
Do you know what day they were planning on doing the lab, or is it in the schedule already?
It's on the schedule as Thursday. Yeah, I don't know why they don't want to give us 2 sections as off the bat, but I don't know why that's a problem. But just sign up so that we can force them. So the sooner everyone signs up, so if everyone signs up today, they're going to be forced to do it. But if you wait till the last minute, they will not open a section.
Have you in 319?
No. I'm going to have to fix that, I guess. Question?
Are you going to do the extra credit thing again?
Yes, I can do extra credit. So we will do that. So extra credit for signing up. And so we'll do probably 5+ points, and we'll put them towards your final. All right, other questions about registration? So register. And I had some poor student last year who waited, and they missed the registration deadline and had to wait like a whole year now. So don't do that. Register early. You can always drop stuff later, but register now. And then I will try, so let's start with just some practice problems. So I promise we do practice problems today. And so let's start with this first one here. And while y'all look at it, I will try to post, I'm going to post the PDF version on the website so you don't have to type everything. All right, so the PDF is up with the practice problems now. So ask your neighbor, ask your friend. If you're not sure how to approach it. Do we have an answer for this first one, or maybe what formula should we use? So you have your cheat sheet, and then you have to look for the keywords because it's asking about half-life. And okay, so that's nice. And then it says the rate constant, and so notice it's a second order reaction, so that might help. And so you can glance at your cheat sheet, at your rate loss summary. I'll pull it up on the computer here. But we're glancing at that, right? It's asking about half-life. So maybe we can just use this formula. I see a lot of blank faces. All right, some nods. Waking up. And so, yes, like I swear this chapter is not as hard as it seems. We have our cheat sheet, so now we can just plug in with that formula. So T half-life for our second order reaction is 1 over K times our A original. And so now it looks like they gave us all the data that we needed, because it says, okay, we have an initial concentration. It's in molarity. And then we have our rate, so we can plug that in. So now we just plug in the values. And let's see, forgot to fire up my calculator. And then just make sure you enter everything properly in the calculator. That's one thing I noticed on the exams, or a few calculator mishaps. And then do we get this number? And let's see, that's 8 to the 1, 2, 3, 4, 5, 6, 7. So it equals 8.3 times 10 to the 7. And then that gives us time, so seconds, based off of our rate law being in seconds. Questions about that one? let's try this next one. So now we have the half-life of a reaction of compound A to give compounds D and E is 8.5 minutes when the initial concentration of A is 0.15 molarity. How long will it take for the concentration to drop to 0.03 molarity if the reaction is either first order or second order? So let's just start with A, and then we'll check in with everybody. So what would it be if it's first order? So again, ask your neighbors. Everything you need is on that cheat sheet. I'll put it out if anybody snuck in and I missed them. See, do we have answers yet? So how do we approach A? What do we know? What did you whisper? So it's first order. And so let's look, okay. So these are kind of our options here for formulas. So we have natural log of some point in time that we're interested in over our initial concentration equals to negative KT. So let's just write that down. And okay, so this looks nice because we care. It's telling us we have an initial concentration of this, so we could plug that in. And we're trying to find T, so time for when it's going to drop to 0.03 molarity. But what's the part that we're missing here? So we're trying to solve for T. We have these two values. So K. So how can we find K though? So back to our first order. And also, what did it tell us? So it says the half-life of a reaction of compound A is 8.5 minutes. So now if we go back to these formulas, is there something we can use to find K then? Yeah, and actually you don't even need to do that. You could just leave your units as minutes. It's not wrong, but yeah, might make your life easier. But exactly, so we can use this formula then, so let's do that. So again, that means our T half-life is equal to ln2 over K, or the 0.693. That's the same thing. And so we have our T. And so I like that you said convert it to seconds, just because you need to be aware of your unit. So if you convert it to seconds, that's perfectly fine. Just keep it written out. Same thing, if you keep it in minutes, make sure you note that it's in minutes, since it's an odd. We don't always work in minutes. 0.693 over K. And so my K is going to be in minutes. If you did it in seconds, then it will be in seconds. And so I get a rate of 0.0815, and that's going to be per minute. And you can always check your sanity on your units, so your rate should just be a per unit of time rate. And so now that we have K, and again, you can be in seconds. There's nothing wrong with that. You should just get your time in seconds. And so now we can plug everything in. So now we have natural log. So we're interested in how long it takes to get to that concentration. So 0.03 over 0.15 for our initial molarity equals negative KT. And I'm just emphasizing that we're in minutes here. And so now we just have to plug in and solve. And so I get like 19.7 minutes. And let's see. So does that mean you got like 1,184 seconds? Awesome. So 19.7 minutes, or 1,184 seconds. Any questions about that one? So now you saw how to do it for first order. So now let's repeat the problem and accept, what if it's second order? So how would that change? the time that it takes. I'll give you all a few minutes to do that. So at least start walking me through this. So what do we start with for part B? So I see pointing at the cheat sheet. So we looked at our rate. So we have kind of two different options. So probably want these two formulas. And so this time let's start with our rate. So we know we need to find K again probably. And so our T half-life is 1 over K over times 1 over our initial concentration. And so now plugging in, so 8.5 minutes, I'm just going to keep mine in minutes, is equal to 1 over K times 1 over our initial concentration. And so do we get this answer for K? 0.784 minutes. And then we can always double check our units. So our K should be, and this makes sense from our formula here, so it's now per molarity per second, or per minute now in our case. So per, oops. So just to keep track. And so now let's go back to our cheat sheet. And so we want to know what the T is to get to that second concentration. So let's copy down this formula. So 1 over A at whatever time we're interested in is equal to KT plus 1 over our initial concentration. And so now we just have to plug in our values. So 1 over 0.03 is equal to 0.784 times T plus 1 over 0.15. And so what do we get when we solve for T? Algebra. So I have 26.66 is equal to 0.784 T. So I get a T of 34 minutes. Is that what other people got? No? Did other people get 34? No, did you find an algebra error? Any questions on this one? Nikki, did you find your error?
Nope, not yet.
All right, we can come back. All right, let's take a look at this one. And again, if you need help punching something into your calculator too, just let me know. Now's the time. And so let's try this one. And so recently a skeleton of King Richard III was found under a parking lot in England. If tissue samples from the skeleton contain about 93.79% of the carbon-14 expected, what year did King Richard die? And the half-life is 5,730 years for carbon. have answers for this one? So punching away. So what formulas might be helpful for this one? So we know we're doing a half-life problem. And so which ones did they say to use when we're just doing like a standard half-life decay problem? So I see some ones for first order, I presume. So that would be correct. So we're looking at these two formulas again. And so let's go back to our problem for a second. And so once again, it seems like we have this issue where we don't have K. So let's go ahead and solve for K again. So using, again, the same formula for our first order, our T half-life is 1 over K times a 0.693. No, I promptly forgot the formula. And so we have half-life, so we can solve for K. And our time can be in years, that's fine. Years, 0.69 over K. So that means my K is going to be in per year then. So then do we get this for K 1.12 roughly times 10 to the negative 4 years? Oh, yeah, I just noticed I had a little bit of dyslexia apparently. So 0.693, sorry, I entered in it backwards. Which, does that look better? 1.2? So good job catching me. All right, so 1.2 times 10 to the negative 4 years. And then, so it's telling us we want to find it when it's at 93.79% of the original, basically. And so what we can do, we'll use this formula again, and we'll plug in the 93 for our point in time, and then we can use 100 as the initial point. Let's go ahead and do that. So I'll just rewrite it first. And so double check me, of course. And so I get a T of about 530 years. Awesome, I see nods. And so I assume that he would have been around in the 1500s, King Richard then. And so according to Wikipedia, King Richard was King of England until 1485, so pretty decent. Questions on this one? Feeling good about these? No problem. All right, let's try some more of these. We'll do a different type of problem. And so in the nuclear industry, chlorine trifluoride is used to prepare uranium hexafluoride, a volatile compound of uranium used in the separation of uranium isotopes. And so chlorine trifluoride is prepared by this reaction of 1 equivalent of chlorine plus 3 equivalents of fluorine to give us 2 equivalents of chlorine trifluoride. So write the equation that relates the rate expressions for this reaction in terms of disappearance of chlorine and fluorine and formation of the chlorine trifluoride. So do we get an answer for this one? And try not to overthink it either. So what is it asking for? What is rate, just generally? And just think back to like the first page of the lecture notes, right? We're talking about defining rate, just a change in concentration over some time. But then what's the factor that we have to account for? We talked about it here. Basically this sort of thing. What are all these numbers? Yeah. So then what can we write for our expression? So let's just start with chlorine. And so what's the rate of that? How would you write that? Exactly. And so in this case, right, it's just a coefficient of 1. We don't need to do any other accounting. And then, right, we're just trying to relate them all. So that was good. You had the negative there since we're going to be losing our chlorine. And so the rate that chlorine is disappearing at, that's going to be equal to our rate that fluorine is disappearing at, except what do we have to account for? What's the little difference for fluorine now? There's 3 of them, exactly. So how is that going to affect the rate? So it's going to be disappearing. Yeah, and then how do we write that? So we have our change in concentration of fluorine over delta T. And then what do I do with the coefficient? So in the bottom. And then don't forget the negative sign like I almost did. So good. And then the last part, so the formation of the chlorine trifluoride. And so I'll at least start with the change. Chlorine trifluoride over delta T. And then what do I need to put for the coefficient? 2. So 2. And once again, that goes on bottom since it's forming at basically twice the speed that chlorine is losing. And so to make the rates equal, divide by 2. And then I just put a plus sign to emphasize that it's being created as opposed to these being consumed. Excellent. So that's all I wanted for this problem. All right, so let's try this next problem. So we're given this process. So we have carbon monoxide plus nitrogen dioxide gives us CO2 plus nitrogen oxide. And they told us that the rate law, so they must have determined this experimentally, but the rate is equal to K times the concentration of nitrogen dioxide squared. And so see if you can determine, so what would happen to the rate law if you decrease the pressure of NO2 from 0.15 to 0.25, and then what happens when you increase the concentration of CO. So I'll give you all a few minutes to think about that. So what do we get for A? So we said it's second order with NO2, and we went from 0.5 ATM to 0.25 ATM. So what's that going to do to the rate? Exactly. So a decrease by 1/4 of the original, or by 4 times. And so you could either do that 2 different ways. So you could just kind of see, well, this went from half, so we just half this, but then it's a factor squared, so then square that gives me my 1/4 factor. Or you could, plug it in, so your rate is equal to K, and then just plug in your values. And of course that cancels, and that would also give you that your rate was 4 times as less. Questions about A? And then what happens if we increase the concentration of CO? So no effect. And so again, it goes back to the rate law. CO is not in that expression, so it has to be 0 order. So no effect. Questions about that one? All right, let's try this next one. So regular flights of supersonic aircraft in the stratosphere are of concern because such aircraft produce nitric oxide. I'll ignore that call. As a byproduct in the exhaust of their engines. Nitric oxide reacts with ozone, as it has been suggested that this could contribute to the depletion of the ozone layer. The reaction NO plus ozone gives you nitrogen dioxide plus oxygen, is first order with respect to both NO and ozone, with a rate constant of 2.2 times 10 to the 7th liters per mole per second. So what is the instantaneous rate of disappearance when the NO concentration is 3.3 times 10 to the negative 6 molarity, and ozone is 5.9 times 10 to the negative 7 molarity? We get an answer for this one. So how do we approach this one, or what's it asking us to do? So think back just what, right, your rate expression is. So it's just whatever rate times your K times your concentrations. And so we go back to this problem. So that means we have some rate is equal to, and they gave us a rate constant, so that's good, K. And then it tells us it's first order. And so we know the instantaneous rate depends then just on the concentration. And so at this point, we can just plug all the numbers in, so we have everything we need. And then we don't have to account for anything, so it's just a 1 for its coefficient. So whatever rate we find will be equal to that rate of disappearance. So let's go ahead and plug that in. Times polarity. Oops. What did I do? Let's see. So did you get 4.28 times 10 to the negative fifth? So I see some nods for that. And then, so units, so moles cancels, one of the liters cancels, so that leaves us with moles per liter second. Any questions about that one? Sorry, I'm just rewriting my 4. All right, let's try this problem. So now we're looking at nitrosyl chloride decomposes to NO and chlorine, so given here. So determine the rate law, the rate constant, and overall order for this reaction from the following data. And so this is concentration of your nitrosyl chloride and the rate. So what are we thinking for this problem? Walk me through your thoughts.
So when we doubled the molarity, we quadrupled the reaction rate. So it's the second one.
Very nice. So I assume you looked at these two pieces of data since they're kind of the easier ones to compare. So, yep, that was probably the easiest way to start. So then we can say it's second order. And let's see, so what else do they want us to do? So let's write the rate. So we just have our rate then is equal to K times our nitrosyl chloride squared then, since y'all told me it was second order. And so then let's go ahead and figure out the rate constant. And so we could plug in any set of data. I'm probably just going to use the first set because it looks like it's the nice numbers. But either way, we should all get the same answer. And I'm just going to plug it in so I don't make any decimal errors. So do we get this for the rate then? 8 times 10 to the negative 8. And it's going to be in, so liters, moles, hour, based off of there. Yeah.
Can you go a little fast, 5 second order?
So the easiest thing to do is just kind of compare these two. And so what you could do, you could just divide, so 3.2 times 10 to the negative 9 divided by 8 times 8 to the negative 10. So this tells you, so this is like the inspection method. If you look, so this doubles, but then this rate quadrupled. So then there you can tell that it's second order. Or there's also kind of the more mathy approach. So you could take rate 2 over rate 1. So let's just do that. So let's say it wasn't as obvious to you what order it was, or maybe you just were given like the 0.2 and the 0.3 data. So you could take your rate of this one, so 0.2, so n over 0.3 n, since we're trying to solve for n, is equal to, then you put over which rates, so you would compare, I should have done 0.3, let me flop that. This is just to make my life easier. So again, this is a mathier way, but then you can solve. So then we're given here, and then you could take the log of each of those. And log of 0.3 over 0.2 is equal to log of that. And so let's do, so log of 0.3 divided by 0.2. And so 0.35. And so you solve for this, and so you get n equals 2 from that mathy method. And so either way, so either by inspection or by plugging in two random values, you should get a second order.
Where'd you get the 0.3 and the 0.2?
So let's start from here. So we have, I got rid of k's because k's canceled. And solving for this gives me 2.25. And then you take the log of both sides so you can get the exponent down here. So then you have n, which is whatever order, times the log of 0.3 over 0.2 equals, so if you take the log of one side, now we have to take the log of our other side. So log of 2.25 gives you 0.35. And then I just divided, so the log of 0.35 divided by the log of 0.3 divided by 0.2. So you can see the calculator. So that gives you 2, so leaving you with n equals 2 there. So yeah, obviously slightly mathier approach, but maybe you'll need to use it, I don't know. But otherwise, kind of the inspection method tends to be easier for most people, myself included. And I'll add in, so that's the log of 2.25. Questions about this one? All right, let's do, I know we're almost out of time, but let's do just one more last practice, and then we'll do break and quiz. All right, so nitrogen monoxide reacts with chlorine according to this equation. So 2 equivalents of nitrogen monoxide plus chlorine gives you our nitrosyl chloride again. And we're given some concentrations and some rates. And so what is a rate law that describes a rate's dependence on the concentrations of NO and chlorine? So what's the rate constant and what is the reaction order? handout is there. All right, we're gonna start it with that. So let's hear your thoughts at least. So we have some generic rate is equal to K times whatever NO to the power of whatever order times chlorine to whatever order. And so walk me through what you noticed or what the orders are. So NO we said is second order, so I assume, so we look at the first two sets of data. This doesn't change, so that's good. And so just focusing on NO, so this doubles and this quadruples, so that's a good clue that that's second order. And then what did you notice about chlorine? First order, second order, 0? So let's see, so looks like 2 to 3, NO is being held constant, so this doubles, and looks like this also doubles. So yeah, I would say first order. So, excellent. And so then it says, so now we need the rate constant, so we can plug in any of these values. So I'll just take the first one out of, I guess, laziness. And so now we just have to plug in the concentrations at whatever one you picked. You can pick the last one. Those might be easier numbers now looking at them, but either way, we should all get the same answer. So do we get a K of 9.12? Which now I'm realizing, yeah, this would have been the much easier values to use. I'm trying to go for lazy, but so K equals 9.12. So liters, molarity, hour. Oops. Questions on that last one? All right, let's go ahead and take our little 10-minute break, and then we'll come back and do our quiz. And I'll also hand out the exams while you take a break and quiz. And of course, if you notice, I would just double check my addition, make sure that there are no grading errors. I'm not perfect, so just let me know if there are any issues. Yeah, I will happily take homework. And then if you snuck in late, I have kind of the chapter 16 cheat sheet up at the front for your enjoyment.
outreach. And we're not running ice cream.
People just want to see ice cream shit blowing out. And greenhouses. I know, we don't get a greenhouse. So.
I mean, imagine how cool it would look if we had a greenhouse
Oh,
under your
is it?
wild
What was
state.
it? Like 5 hours in charge.
Wait, that's what was supposed to happen.
I know. I'm bitter.
I know. They don't want to give a shit.
I don't know. It was like, it would always be like, oh, it was what's. Oh yeah, that whole crash.
All right, I'll go ahead and hand out the quiz. So as usual, open notes, show your work so I can give you partial credit. I don't think you really need them until maybe the end, but let me go get some. Oh, and I'm gonna stop streaming.